please make sure that you have installed everything, and also feel free to raise your hand in the chat if you have problems like during the installation. So for the sake of time, I just start the presentation, and we will have a checkpoint where we just make sure that everything is cool for everyone. Okay, so I have 2.8. I think you should make sure that you have 3.7. Yeah, for Ethan Lee, who asked the question. Yeah, so there is if there's any question or concern from the host, I would be happy to answer it right now. If not, I can start sharing my screen and starting the presentation. Okay, I think it's cool. So again, I'm Arash. I work with Professor Nikolai Tanasov in Existential Robotics Laboratory, UCSD. Today we are going to talk about localization and mapping. First of all, I want to go briefly about robot autonomy. So basically, when it comes to robots, every task can be essentially broken down to four components as sensing, where we use a bunch of sensors, let's say depth estimation or depth sensors or RGB sensors, radar, LiDAR, to just sense and gather some data from the environment. And based on the environment, environment measurements, we build a model or estimate a model of the environment. Again, based on the application, it varies. It can be a map of the environment. It can be the temperature of an object, whatever, based on the application. And then we always have some kind of cost function or reward function that we want to maximize or minimize. So basically need a plan to do our task or do our maximization or minimization. Let's say for an exploration task, let's think of the Curiosity robot on Mars, which is Explorer robot. So for exploration, basically it means that where should I go like for the next like time step. And based on the plan that we choose, we use some bunch of actuators to execute the plan, as for example here. Today we are going to talk about estimation and sensing, basically the perception part of a robot autonomy task. And in the next workshop, my colleague Tianyu is going to talk about planning and maybe a little bit of action. So let's have a very brief review of probability, first of all, because that's going to be used like during the presentation. So for an event in the sample, event A in sample space omega, where sample space omega is basically the set of all possible events, we assume that the probability of an event is always a non-negative number. The probability of sample space, which I said, basically means that probability of something happens is always 1 because if something happens at the end of the day, always. And for a bunch of mutually exclusive events, the probability of the probability of their union is equal to the sum of their probabilities. And that results in three corollaries. First of all, probability of nothing happens is 0. Like basically here, the empty set means nothing happens, and the probability of two events is always bounded by the probability of their union, also bounded by some of their probabilities. And probability of event A is less than equal to probability of event B if A is a subset of B. And also, I just super fast go through a bunch of probability formulas that we will use. Total probability, which says we can break down the probability of B event B as sum of probabilities of B and A, where A is a partition of the sample space. We have the definition of conditional probability. We have Bayes' rule, very important formula, which basically helps to flip the conditional probability. As a rule of thumb, this is very, very useful when it comes to incorporating bunch of observations into your estimation. Always people use Bayes' theorem. And as a result of total probability and Bayes' theorem, we can have basically some kind of modified version of the Bayes' theorem. And also another important concept in probability is independent events. Uh, Events A and B are independent when probability of A given B is again is equal to probability of A. Basically means that B doesn't bring any information about A. Another form of writing independent events is that probability of A and B is equal to the product of probability of A and probability B. This is more important from a computational point of view. And also, you can think of why, but actually these joint events or mutual exclusive events are always dependent, as many people may like think that as a misconception actually, that exclusive events are independent. That's not the case. Exclusive events are always dependent actually. So yeah, that's about it for probability review. We get into basically the main part of the presentation. We start by mapping. So what is mapping? Mapping is nothing more than a way to represent your environment. And there are many ways to represent your environment, many sensors that you can use, applications that dictate how you're going to represent your environment. For example, you can represent your environment with some point clouds. Basically, it just as the name suggests, it's just a cloud of 2D or 3D points which show the surface of an object. The other way is landmark based. You can think of landmarks as some kind of QR codes or corners of an object, places that are easier to track, let's say from like a vision perspective. Uh, Landmark based mapping is basically just trying to map those regions or points of interest. We can go to like more complicated representations like circles, where we try to represent a surface, for example, with a bunch of circular plates. Uh, these are all like dependent on your application, available computational power, etc. For like, I mean, it's up to you to choose which kind of representation you want for your robotic task. And so one thing about like a sparse representation is that it's sparse, as the name suggests. So there's always some kind of empty space between elements of the environment. On the other hand, we have dense representations where we have a continuous, basically the elements are placed continuously. There is no empty space for the most part between the elements, like occupancy grid map, which is basically some kind of, we can think of it as a pixelized map, or basically an image where each pixel tells about the occupancy or being free for each cell. More complicated representations are sign distance fields, where basically you can partition the whole space into outside of this object, on the object surface, and inside of the object by the sign of the distance to the closest point to the object. So if you think of the left part as the image itself, the sign distance field of an image becomes something like the right hand, where in the red zone, we have positive distance. On the black zone, we have zero distance, basically means it lies over the surface. And in the green area, we have the like negative distance. So that's why it's called sign distance field. Signed, it comes from the inside, outside, or over the surface. Also, as you may be familiar with, we have polygon meshes, which basically you can use some kind of triangular or hexagonal or whatever kind of net or mesh of polygons to represent 3D object. And you can always adjust the resolution as well. So in summary, mapping is building some kind of knowledge, which I call it map, using robot trajectory and robot observations. So robot trajectory basically means the position of the robot, or more specifically, position of the sensor over time, and the observations made from those positions over time. What we are more interested today is to talk about logouts mapping for 2D robots and LiDAR scanners. So when it comes to 2D robots, we have the X and Y position and theta orientation of the robot over time. So this notation means from 1 to t, like from time t equal to 1 to t equal to capital T. And for LiDAR scans, which is essentially some kind of range measurements, we will talk about it in more detail later. And at the end of the day, we make some kind of probabilistic representation of the map. It's an occupancy grid, just like this image here on the left, but it's more fancy actually. It is probabilistic. So it tells you the probability of each cell or pixel being occupied. So let's talk about the LiDAR scanner. So LiDAR stands for light detection and ranging. Uh, how a LiDAR scanner works is basically it's radiates pulsed laser light and measures the time of return and the frequency of the reflected pulses in order to estimate the range of the emitted light in order to get some kind of depth estimation. So what we are more interested in from a computational point of view is the output of the LiDAR scanner, which is basically a bunch of range measurements with their corresponding angles. So in the picture on the right, you can see a LiDAR scan, which is basically some range measurements. Also, you have access to the angles of each measurement. So
sorry for interrupting. There's a question in the chat. So Rai said, "I'm lost, LOL," and I agree. So I feel like we're going over too much. Do you mind focusing on kind of what is the basics? So go back to the previous slide and give us more information on what is X here, what is R, what is psi.
Yeah, we will talk about we will talk about them later in more details, but just to briefly review it again, let me just make sure. So okay, let me just make some clarifications here, which may be more confusing. So we have a bold font X and Z here, and we have a normal X here. So by bold font, I always mean during the whole presentation, bold means a vector, which basically can be written as several elements. That goes for bold X and also bold Z. And just to talk more about the elements of logouts mapping problem here, uh, X, Y, and theta basically can completely indicate a robot position in the 2D plane. So if you think of a 2D plane, like let's say an occupancy map. So we have an X dimension, we have a Y dimension that tells you the position of the robot, but still we are also interested to know about the orientation of the robot, because when it comes to sensor measurements, the orientation matters. And so that's why also we take into account the orientation of the robot. You can think of the robot and sensor interchangeably here. We always think that robot is the sensor in the whole presentation. And for LiDAR scans, I think I can
yeah, so sorry. Yeah, by the way, this is meant to be interactive, so questions are very welcome. So Arash, do you mind if I give a little more information?
Sure, yeah.
Do you mind letting me share my screen for a second?
Yeah.
I think I am not a host. Is it possible that you guys make me a host as well?
You should be a co-host, Professor.
Still does not work. Okay.
You can ask me to switch slides if you. I can just share my screen.
No, I wanted to draw something. I think
okay.
that's, but I'm not able to access. Okay, let me try it this way. All right, do you guys see
working.
this? Okay,
Yeah, it's working.
So we have a robot, and it's just given by its x and y coordinates. Okay, so we have some coordinate frame, and x, y over here is the position of our robot, and we have a environment over here. Okay, sorry about that. Do you guys mind enabling actually everyone to share? I think people will be nice, or at least for a moment, so that I can draw something. Is that possible?
That should be available.
Oh yeah, that's a good point. We can all annotate. So let's see if I can do that. Yeah. All right. Great. Okay. So good. I think we're good now. Can you guys see everything now? All right. So we have the robot over here. Okay. So this is X, Y, and we have some environment like this, which is unknown. So we don't know what's here. So our robot will try to make a map of this environment, and the robot has a sensor. So as Arash was showing, there's a LiDAR sensor. So what is a LiDAR sensor? It's something that shoots beams like this and measures the distance from whatever the beam hits. So let's say there's some object over here, some object over here. This LiDAR will measure the distance from the robot's position to the first obstacle it hits along the way. So we can think of, let's say our LiDAR has these 4 beams. It will return to us a vector of measurements. Let's call them Z1, Z2, Z3, and Z4, which correspond to the distances. So this here will be Z1. This here will be Z2. This here will be Z3. And this distance here will be Z4. Okay. So if the LiDAR doesn't hit anything in the environment, which is very possible, right? If you're looking down an open hallway, there might be no obstacle along the way, in which case our sensor has some kind of a maximum range. So instead of infinity, it will give us a maximum value. So let's say 3 and 4 didn't hit anything, and the maximum range of our LiDAR is 30, then we get a measurement of 30. And then for the other 2, we'll get something like, let's say 2 and 3. So our measurement at this time might look something like this. And I see more questions in the chat. What if there is a height that the robot cannot see on the 2-dimensional plane, but would be an obstacle for the top part of the robot? Do you mean something? Oh, I see. So it's something above the robot. Okay, so we'll simplify things for now, and we'll only consider things in 2D at first. So we'll get to the kind of the 3D case a little later. And I see one more question. Does the LiDAR return an angle value so we know which direction? Yes, great question. So the LiDAR also, we know at what angle these rays are being sent out. So essentially we know this is an angle alpha 1, alpha 2, alpha 3, and alpha 4. Okay, so those angles are actually known and fixed in advance. They don't change for our sensor over time. So they're always fixed. So the LiDAR always sends these rays out at a fixed angle in the robot's frame. Okay. So in addition, the robot might have orientation. So that's something we didn't mention so far. So typically we would model its the robot's position might have orientation as well. So we have X and Y are the robot coordinates, and then theta is the orientation of the robot. So if the robot is facing this way, so let's say our LiDAR has 4 beams, they're always kind of done this way. 1 second. Let me draw more here. Okay, so for example, if our robot is facing this way, we might have our 4 beams go like this. Okay, and if the robot is facing this way, we might have our 4 beams go like this. Okay, so they always have a fixed angle with respect to the robot's orientation. So now, again, to go back to what Arash had in the slide, he said that we represent our robot with X, Y, and theta. So theta is this angle here from the x-axis to the robot's current orientation. This is theta, and x and y are the position of the robot. So this is the how we represent our robot. So these are 2 scalars and 1 angle. And in addition, we have the LiDAR measurements, Z, and I think Arash called them R instead of Z on the slide. So sorry, to be consistent, we have something like R1, R2, R3, and R4 are the measurements, and then alpha 1, alpha 2, alpha 3, and alpha 4 are the angles associated with them. Okay, so does the measurement model make sense so far? And I see more questions here. Does the LiDAR require a robot to have a lot of processing power and memory for the controller? Yeah, good question. So the LiDAR does not require too much. It has some power requirement, but as long as you have a battery to power it, it will provide this data directly to you. So you don't need too much memory or processing power. So the question is, what do we do with these measurements? We'll actually be getting many of them over time, and we can think about how to use them. And whether we store them in memory or use them for something is a decision we can make. Another question, is the angle that the LiDAR returns absolute or in reference to the robot's theta? So it's in reference to the robot's theta. So the angle is always fixed, and it would be something like, let's say, minus 5 degrees, 5 degrees, let's say minus 15 over here, and 15 over here. So this is always fixed. So again, this is 5, minus 15, and 15 as an example. So these will always be fixed. Okay, does this make sense so far? All right, good. So we have the robot's position, orientation, and our LiDAR sensor. And let's look at one more thing. So now we have this unknown environment, right? We will imagine we're in 2 dimensions for now, as someone mentioned earlier. So the environment has obstacles or objects in it, and we're going to try to build a map. So our map will consist of boxes over here. So we're going to split the whole environment into a regular grid like this. All right. And then for each of these boxes, I'm going to try to say, is this 0 or is this 1, where 0 means free and 1 means occupied. Okay, so if my robot is over here, so our robot doesn't have to be exactly on this grid, right? The robot can be somewhere in a continuous space. So let's say my robot is over here and it's oriented this way, right? Which says it has position and orientation. Let's call this is our x-axis and this is our y-axis. All right. Then no, so we'll actually not keep the grid infinitesimally small. We'll have some known resolution for the map, and we're gonna see this later. We're gonna have some value epsilon here, which is the map. We're gonna call this the map resolution. So we are gonna see soon in the demo how we actually define the map. We can define the kind of the minimum value over here, the maximum value over here, and the resolution, which will tell us how many of these grid boxes we have. And same for the, so we can assume that it's epsilon on both sides here to keep things simple. So each box is a size epsilon by epsilon, which could be something like 10 centimeters. So this is how we model our map. Okay, so then when we use our LiDAR sensor, it will give us some measurement to things in the environment, as we said, along these 4 beams. And we can figure out kind of the places where the LiDAR hit. It's very likely that these are occupied. So we can do the math and kind of, we know the distance that the LiDAR measured for us and the angle at which it measured. We can figure out which box this corresponds to and mark this box as occupied. So let's say over here, over here. Over here and over here. And as the robot is moving over time, so let's say my robot moves around, I will be in a new position. I'll get a new LiDAR scan, and I'll mark new locations as occupied if they are. Okay, so let's say over here and over here. So I see a few more questions. What if there's an object between the squares? Would both squares get marked as occupied? And this is up to the implementer, says Ashwin. Yeah, so if there's an object right in between, so that would have to be like some, or you mean if it's a big object, right? If we have some very big object over here, as our LiDAR is observing it many times, we're gonna keep marking more and more boxes of this big object. So in practice, our LiDAR has a lot more than 4 rays. A real LiDAR has something on the order of hundreds or thousands. So the LiDAR that Arash was showing had something like 600 rays or something like this. So we'll actually be hitting many of these boxes. And we'll be updating the map over time. Okay, so I think let's switch back to the slides, but Arash, keep it much more high level. Don't worry about the details. We don't have to define all the probability and things like that.
Sure.
Show how the robot moves over time and how the map is updated. And I think we can do the demo soon so that people have a better sense of what we're talking about.
Yeah, sure. Okay, can I switch to, okay, thanks. Let's see, okay. So just taking off from what Nikolai explained. So if you remember, Nikolai said that the rays hit obstacles. So one of the problems when it comes to finding the obstacles is to find their geometric position. As mentioned previously by Nikolai, so let's have a robot with x, y, theta as robot position and a range measurement of r and phi, where r is the range and phi is the angle between robot's orientation and the ray or the beam. So let's say we have a beam that has hit something, let's say an obstacle, and the robot itself is at position xy, orientation theta. The problem of finding the position of the obstacle in the word frame or in the xy coordinates of the obstacle is basically changing from polar to Cartesian transformation. As here, it's basically a bunch of like trigonometrics to find the position as shown here. So let's start with the demo. Basically, we are going to run a script that does the mentioned functionality. So I just want to first make sure that everyone has everything installed. If not, please mention your problem in the chat.
Yeah, so first step is to download the code from this GitHub repo. So if you have used GitHub before, you should already know how to do it. If you have never used it before, in the top right, there is a green button. Arsh, if you go up a bit, right there, code. You can even use download zip. So this will download all the code for you, and will let you have it. So that way you have it locally on your computer, and then you can go to the instructions. So Arash, do you want to show. So here are some instructions for actually installing Python if you don't have it yet on the first page. And if you already have it, we should go to the demo. So Arash, how do we get to the demo?
Yeah. So first of all, make sure that you have cloned or downloaded your repo, just as Nikolai said, and then open a terminal, go to the directory of the downloaded repo, and write down these two lines. The installation line may take something like 30 to 40 seconds, so you should wait a little bit. I just want to first make sure that everyone is in this step, because the next step is basically just running the code. So
what should people do if they don't have terminal?
People who don't have terminal can basically make, based on their operating system, I can give them individual instructions. So let's see.
I'm sorry, it's mentioning a zip file. What kind of zip file are we talking about?
Yeah, Arash, do you want to show how to download the zip file?
So you click on download zip.
So are you on this web page where you can see this green button that Arash is showing?
Is it the README page?
Let me put the links in the chat again. So
README.md.
no, if you go to the home page, so essentially, if you click on this link, when you open this, you should see exactly what Arash is showing on the. Oh, sorry, I gave you the wrong link. Yeah, let's try now too. Yeah, so sorry about that. Okay, so this is the link. Yeah, I just the latest one I put in the chat. So if you click on this, you should see exactly what Arash is showing on the screen. Can you see this?
Sorry, so I just downloaded the PyCharm and the zip file. What do I do from there?
Okay, so I guess you should install PyCharm first if you haven't yet. And then once you have PyCharm installed, you should be able to, you should also unzip this file. And once you have both of these done, you should be able through PyCharm to access what's in the zip.
By unzip, do you mean extract? Like you
Yes,
right-click?
correct. Yeah, unzip and extract is the same thing. Yeah, I think any IDE should work as long as you have Python installed. So if you don't have Python installed, that would be a problem.
And then once you extract it, what do you do from there?
So do you have PyCharm and Python installed already?
Yes.
Okay, so then you can start PyCharm.
Yep.
And then from inside PyCharm, Arash, what should he try from PyCharm?
Yeah, from PyCharm, click on the. I can show you here actually. You might see.
You can show what to click there.
Open or new project.
Not to create a new project, you should click on open and go to the directory of your downloaded Python, downloaded GitHub repo. So let's say if I.
Sorry, what?
Can you hear me? If you have, let's say, downloaded the repo here, you should just click on it and it makes a virtual environment by itself, basically. So I just want to make sure, has anyone been able to run one of the scripts? Please mention in the chat if you have. You can go to the, I don't think anything, I mean, they may work, but you might get some errors. Yeah, the script is the one that mentioned by Kunal in the chat, and you can also run the script from here. You should go to the wiki page and basically run the script for demo 1.
Could you show us which file exactly we're supposed to?
Yeah, Arash, do you want to go step by step with starting with PyCharm?
Okay, do you have the PyCharm installed and open the project?
Yep.
Okay, cool.
I'm trying to find it, but it's like it's hard because I don't know what I'm looking for.
So do you have the PyCharm open? Like,
yes.
let me, do you see this screen?
Nope.
In your PyCharm?
Nope.
You don't see that. Okay.
There's something simple. It says welcome to PyCharm. And it says new project or open.
Open project. You should click on open project.
Uh-huh.
Okay, click on this and go to the directory where you have downloaded the repo.
Yeah, but like the zip that we extracted, right? Go there.
Yes.
But which file exactly am I supposed to open?
Just click on the folder that you have extracted. That's all you need to do.
Okay.
Let's say I have downloaded it here. Basically, just click on the folder and click on OK. That's it. Just tries to build the environment for you. Does that work for you?
Let me see. Yeah, I think so. It says leading components.
Okay, good.
Thank you.
You're welcome. Okay, so
yeah, no, this is great. If anyone else has questions, please say. And that's the point of this, that we kind of all get the demo to work. So if you're stuck anywhere, please write in the chat so we know. And if you're also successful, also write that in the chat so we have some feedback of how people are doing. So if you got everything to work in demo 0, then say yes, I'm good. If you're lost and you don't know where to start, write that too so we can help you.
Is Python 3.8 okay?
Yeah, you might have to do some modification as people mentioned in the chat, but it should work. So if you get an error, let us know and we'll tell you what to how to adjust that.
Sure. Thank you.
So Ethan, all the demos are on here. I think for now we're going to do only demo 0. Is that the case, Arash?
Demo 0 and demo 1. Demo 0 is basically the same as the installation instructions. So they can start with demo 1. Yeah.
Yeah, so Ethan demo 1 is in the link I just posted.
The error for undo, I think it comes from the fact that your Python directory is either doesn't exist, meaning that Python is not installed, or I think it's not just configured correctly. So can you run Python from command directly? That would solve the problem actually. You can open Python. Okay, so you can basically open through Python, you can run the scripts. You don't need to do any other steps. Just follow the demo 0 in the wiki page, and then you can run the code by the script in demo 1.
So Ars, do you mind showing a demo of this too for people
Sure.
who are running the demo from the terminal?
Oh, yeah, sure.
Is this the command prompt? Like we are supposed to use the command prompt on
You can
Windows?
use both command and PyCharm. It's up to you, whatever you're more comfortable with. Okay, for people who use command, you can basically, let me just make sure. You can basically open a terminal at the directory or change your directory to the extracted zip file or cloned repo, and then make sure that you are in the environment. So that's how you get into the environment, virtual environment. So this is equivalent to what you need to do in demo 1. So Zurabi, have you got pip installed?
I said pip install pipenv, but it still gives me this error.
Oh, that's a very good point. If you are using Python 3, maybe you need to use pip3. If you have both Python 2 and Python 3, you should clarify it like the last message in the chat, basically.
Yeah, try what Kunal is suggesting.
Yeah.
And Arash, while people are still figuring things out, do you mind actually running the demo on your end to show
Sure.
what they should expect to see if it works correctly?
Sure. So basically, when you log into the virtual environment, all you need to do is to run this script. And that's what you should expect to see. So basically, it's a robot exploring an unknown environment and building a point cloud map of the environment. Basically, all the robot does is to find the XY coordinates of the point clouds of LiDAR scans. So Kentaro,
Okay, so I still see some people have errors.
For Kentaro, use the command that Bjorn suggested. That may work. So for Kunal, did you solve your error?
And Arash, do you mind showing again for PyCharm? Because I think people who are trying to use PyCharm could use some help.
So for PyCharm, you basically
you should not give up yet. So follow Arash right now.
So what you need to do for the PyCharm, you open a Python console, which is basically the same as the command line, and then copy and paste the demo code.
Which file am I supposed to open to get this?
Do you have the PyCharm opened now?
Yes, sir. Or is it just the terminal? I click on the terminal down
Just
below.
go to the terminal and copy and paste this script. That does the same work for you.
Leader.cloud.py, right?
Yes. So
Okay,
just make
can't
sure that
open.
you're on your terminal, not Python console. Any other questions?
Yeah, it just says can't open. Can't open file.
Which file?
The one that you told me to copy paste? Or do I put a $sign?
No, I mean, it generates a $sign by itself. So are you sure that you are sitting at the correct directory?
I believe so.
For Joe, you should use the
Yeah,
same
it's
command
open.
at the wiki, as Nicola mentioned in the chat.
Yep, nothing. Same error, actually.
Yeah, so several people are getting can't open file error.
Yeah, just please clarify where are you running the code, either from PyCharm or your command line. For Jack, you can basically do what Bjorn said, and I'm going to copy it for you. You can run the code from other Python versions as well, like I just mentioned here. For Igor, what do you mean by Windows subsystem? Are you using a virtual machine? You can run the code directly from Windows. You don't need to go to Ubuntu, like from Windows to Ubuntu. So Andres, can you run the code? I just want to make sure. Okay, thank you for clarification. And for low P, you should go to the one basically as seen here with the dash, not with the underline. So for Justin, are you using, okay, for PyCharm, basically all you need to do for Justin, go to your terminal and copy and paste the script in the wiki page. This script in the wiki page. And so this is the link to the wiki page.
So after we do CD robotics workshop, like I tried doing pipe NV shell in PyCharm. I just paste it, right?
Oh, no, wait. If you're using PyCharm, you don't need to use pipeenv.
Yeah, you can directly, so skip that step. You can directly try to run this, the latest thing I put in the chat. So just say python-m robotics workshop script lidar point cloud. Is that correct, Arsh?
Yes, yes, exactly.
Okay, let me try. Okay, it's giving me fancier and fancier errors.
So,
It's giving you many different errors.
Yes.
Okay, very good.
Perfect.
can you copy and
It's
paste it in
okay.
the chat?
Sure. I feel like I'm slowing us down though.
No, I mean everyone has problems. Don't worry. Oh, okay. So, okay. The problem is that you haven't installed the requirements for Rayleigh. You basically you haven't installed the. Let me show you. So you haven't used this
Sure.
step. That's why we basically don't have the software for that, like NumPy and Matplotlib.
So I just copy and paste that into the terminal.
Yes,
Okay, where is that again? Installing Python packages. README. Okay,
it's in the README file.
gotcha. Let me see.
Justin, since you're running the code from terminal, you should make sure that you have logged into the virtual environment. Have you used the pipenv shell? Justin, you should use pipenv shell in order to be running the code. Otherwise, you will get no directory errors.
God. I'm trying to directly copy paste, but I don't think it's working.
What's the problem?
Um,
You shouldn't manually install NumPy. The best thing to do is to just follow the instructions in the main page, because that doesn't install the NumPy for your environment. Rarely you don't have pipenv installed, so you should first install pipenv.
After running that pip install command, like I'm running into the case where it's still not recognized because it's not installed globally or something like that. So it doesn't find the path.
Do you have team? Do you have Python 2 installed in your computer as well?
No.
Okay. Can you try pip3 install instead? Everyone who has problems with pipenv after pip installation, maybe you need to try pip3 install.
I tried that. It still doesn't work.
Still doesn't work. Okay. Remove the user modifier from at the end of the installation.
Arsh, is there a poll that we can start from Zoom to see how many people managed to get this to work and how many didn't? I think on the bottom right there might be a way to start a poll.
Let me see. Let me stop sharing for a second. I think I don't have the access to that.
Okay, never mind.
Yeah. Share the screen.
Maybe if people could react with a thumbs up, say, to say that you have managed to complete this part.
Yeah, you can even react in your participants page by a yes or no. Yeah, that basically works as a voting as well.
So
Oh yeah, this is great. Yeah, can you guys look at participants in Zoom? You can see, we can see this way.
So actually, if you all could raise your hands, that way it'll stay up because the other reactions have an automatic timeout. So raise your hands if you are not done yet. Okay, we have about a quarter. Okay, there's still 22 people who are trying to catch up.
Okay, I think since most of the people have been able to run the script, I guess for the people who hasn't been able, I would say please just read the main page for the GitHub repo and try to install everything correctly. Definitely, if you follow everything completely, you can run the code because I just tested it on on Windows and Ubuntu, and things might work if you completely run all of the commands. Just because we are basically very short on time, and yeah, we can definitely try helping other people in the meanwhile.
Yeah, I mean, I think ours is more important that we get
Yeah.
people to get this to run and enjoy the workshop rather than get through everything. But I agree, we can try to go to the next step, and in the meantime, continue to help the ones that are not able to run it yet.
Okay. Okay, we go for the rest of the slides. So for the people who has been able to run the point cloud representation, you might
sorry for interrupting, just one point. Do you mind running it again on your end, just to show what people would see if they, so for those who didn't manage to run it, they can try again later as well.
Yeah.
And feel free to also start issues on the GitHub page that we can try to yeah, you can, we can try to help you later.
Yeah, so basically
do you mind making this larger, Arash?
Yeah, sure. So what the robot is doing is exploring the area. It's a 2D robot, so it's basically has a X, Y, and an orientation. You can see the orientation by the basically some kind of needle at the tip of the robot. And all it does is to using the trigonometry formula that I showed in the slides to find the position of the point clouds for each LiDAR scan and just draw them in the map. So that's one of the actually benefits of using the point cloud mapping is it's very simple. It doesn't need any further computation other than finding the position of the points in the LiDAR scan. On the other hand, the problem with the point clouds is that it's memory inefficient in the sense that the map size grows with the number of observations. We have more points, we have more memory usage, and also there's some void spaces between points, which makes it not suitable for collision avoidance. So that's why we resort to occupancy grid mapping, which, as Nikolai mentioned, we basically divide the environment into regular cells. Each cell tells about the occupancy of the environment. It can be free or occupied, and why not ask what are these gray areas? These gray areas is basically, as you can also see in the demos, is the unexplored area of the map. I'm not going to delve deep into the probabilities part of it. What I'm going to say, high level speaking, is that since we have noise in the measurements and also in the robot location, we need to maintain a probability for the map instead of having a binary like 0 or 1 occupancy value. And so there is a method called log odds mapping, which helps to maintain this probability over time. And basically coming with new observations coming, we can compute this probability. There are some assumptions. One assumption is that map cells are statistically independent. That helps the mapping easier because we need to keep probability or occupancy probability of each map cell separately. I'm not going to delve into the details of it. We can definitely feel free to read it. I can send you the slides to you later. The bottom line is the log odds mapping makes it possible to compute the map occupancy only by maintaining the maintaining the log odds value of the map. What is log odds value? It's some kind of abstract mathematical concept derived from map occupancy. If I show the probability of map occupancy with gamma, log odds of the map is lambda, which is the log, as the name suggests, log of the odds ratio gamma over 1 minus gamma. And all we need to do is to maintain or track values for lambda or log odds for each map cell in order to be able to build a map. And if we, so what we are more interested is gamma, because that tells us the occupancy probability of a map. So if we solve this equation for gamma, we land on the formula for occupancy from log odds value. At the end of the day, what we need to do is to, let's say using LiDAR scanner, what we need to do is to find the pixels of the map where the LiDAR travels through, find the ones that are free, find the one that LiDAR hits, and update these log odd values as in here for each pixel. So this is basically the summary. We cast rays for each observation, and based on the observation, if the pixel is free, we update its log odds value according to that, and it's occupied, we do this again accordingly. So I think it's good to go to the next demo. So then we can also help people who are still having issues running the code. So let's go for the demo number 2, which is basically
And Arash, if I can share my screen again for a second before we start demo 2. I want to show, kind of to summarize the last thing you said. So I want to show people now what was the difference between the first demo and the second demo in kind of what to expect. And so in the first demo, we did something like this. We had the robot with the orientation. It was shooting the LiDAR beams. And then wherever we hit the point, we just found its coordinates in the global frame. So right, we had this R, and we had this angle alpha over here, and we knew the robot orientation theta and the X and Y position of the robot. So R showed us a formula which allowed us to compute the X and Y coordinates of this point. So let's call this XP and YP. So R showed us an expression of how to compute these. And that's how we built the map in the first demo. Okay. In the second demo, what we're doing is slightly different. So we said we're going to place this grid on the map like this, and then we check for every. So let me simplify this drawing a bit. Sorry. doing it again very quickly. So let's say this is our robot. We have a long ray. So this is the light array. And then we have this grid for the map. So then we're going to check for every box whether this line goes through the box or not. And we're going to keep some sort of confidence level for each box, whether it's free or occupied. So this is what Arash was calling lambda. For each of these boxes, we're going to have a lambda 1, lambda 2, lambda 3, lambda 4, and so on. So with each cell, we associate some kind of a confidence lambda. And this lambda starts from 0. So lambda each cell is initially 0. And then if our LiDAR ray says that this location is occupied, we increase lambda. So let's say this is lambda 50 over here. So I'm going to do lambda 50 at time step 1 is lambda 50 at time step 0 plus some little value delta lambda. So if I start at 0 initially, I'm going to add some small value, let's say 0.1. So now at time 1 for the occupied ones, they're going to become 0.1. The ones that are along the ray but were not hit, like this cell, this cell, this cell over here, this cell over here. So all of these that the ray passed through but did not hit an obstacle, for those we're going to subtract the delta lambda. So after the first update, so initially we have everything is 0. After this update, we're going to get minus 0.1, minus 0.1 for all of these free ones, and plus 0.1 over here. Okay, so if we think of kind of the larger values being dark and more negative values being light, we're going to see our matrix that represents the map get darker in the places where the LiDAR hits obstacles, and get brighter or more negative in places where the LiDAR rays indicate that the environment is free. Okay, so this is now what we're doing. Instead of just looking for the points, we're actually increasing or decreasing the values in these cells. So now, Arash, if you run the second demo on your computer, we can see what the output should be, and then we can try to help people get to try to run it on their own computer as well.
Okay, so basically what you need to do, if you follow the previous steps, you need to simply run this script instead of demo 1. I'm going to run it for both in PyCharm and in terminal. So for PyCharm, you need to go to terminal, write down the script and just hit enter. And also you can do the same thing in your terminal and write down the code and hit enter.
Yeah, I think just show one of them. Just show PyCharm for now.
Yeah, this is for both of them. Yeah, so here the robot moves in the environment, and so again the robot is shown by a red dot with a orientation, but unlike the previous time, the environment is it's a grid environment, or it's a rasterized environment, so that you have pixels, and each pixel has already a value. The gray area is unexplored, the white area is free, and the black area is occupied pixels. So the robot takes the previous trajectory, as in the last example, and tries to build a 2D occupancy map.
Question by Mark. So Mark, for logouts mapping, I noticed that this delta lambda is a fixed constant. Is this always the case, or is it an approximation? So typically we actually keep this fixed throughout, and it's determined by the noise in your sensor. So the theory that Arash has on the slides shows that it is something like the ratio of true positives versus false positives. Something like how often does your LiDAR tell you that a particular location is occupied when it's actually free, and how often does it tell you it's free when it's actually occupied? So this delta lambda comes from there. So it's some property of the sensor. So if you can test your sensor in advance, you can actually fix that value, and you don't have to change it online. So I believe in the demo we have some fixed constant, which I think should be log of 4. Is that the case, Arash?
It's log of
Log of 9?
no, it's basically log of e, like the exponential number. Basically, the delta lambda is 1.
Oh, I see.
Yeah.
Delta lambda is just 1 in our
Yeah,
demo. I see.
Yeah.
Yeah, okay, that sounds fine too. But roughly you have something like the ratio of how many times you expect your LiDAR scan to be correct versus how many times it's wrong. So for example, if it's correct 80% of the time, you're going to have something like 80. And if it's wrong 20% of the time, you're going to have 20. So the value will be something like this, log of 80 over 20. So this is log of 4. So I think Arash has picked some numbers that make it nice. But the theory shows that we should be taking a log of the ratio of how many times, what percentage of the time the sensor is correct versus what percentage of the time it is wrong. Okay, so besides installation questions, are there any questions on the difference between the two demos and what we saw so far? I liked Mark's question, so I want to see if there are any more conceptual questions in addition to Git and Python ones.
Yeah, for Mark, it also would make sense. It's depends on your sensor. If your sensor's accuracy decreases with the distance, definitely it's a good idea to decrease lambda by distance. Basically, the type of delta lambda we used here is super basic. Like people use some kind of other like fancier like distance dependent or position dependent delta lambdas as well, which is basically the delta lambda is called inverse observation model. I mean, that's the name you may see in the publications. The video slides would be shared as I've been told. And very good question by Kentaro. Definitely we need an upper or lower bound for lambda because first of all, we don't want the values to get into infinity. And also, exactly as you have mentioned in your question, if the environment is technically dynamic, if the environment changes, it's good to keep some maximum or minimum value for lambda in order to take into account those dynamism in the environment. Delta given by LiDAR product specification or testing. Yeah, it's a number that I basically choose and it's a hyperparameter, so you can adjust it based on your application. And as Nikolai mentioned, yeah, LiDARs are one of the most accurate sensors when it comes to SLAM. Okay, so we are very short on time, so let's just talk about localization a little bit. Nikolai, do you have anything to add for the mapping?
So is the next demo is localization? Is that the case?
Yeah.
Yeah. So explain what's the difference between localization and mapping, and
sure.
and we can get to this demo too. Yeah.
Sure. So let's start with localization. So basically, first I start with a concept called odometry, which is basically using the motion sensors to estimate the robot pose. The problem is that motion sensors have a very small noise, but this small noise actually accumulates over time. So between two consecutive, let's say, time steps, the location is usually pretty accurate, but these small errors accumulate over time and make a huge drift between robot's true position and the estimated position. So simply relying on odometry is not a safe option. It is better to use some kind of external observations like LiDAR measurements as well. So let me see. Uh, in this workshop, we talk about differential drive motors or model only, which is basically kind of robot that can adjust its linear and angular velocity by choosing values, by choosing velocity for its left and right wheels. So basically you can think of a robot that has full control over both left and right velocity for the wheels, and based on that it can adjust its linear velocity and angular velocity. Yeah, exactly. DC or stepper motors are one of the practical implementations for differential drive. Basically you need two motors or a differential with one motor in order to mimic this functionality. And in a simple formulation, the motion of a 2D robot with a differential drive follows from these equations. Basically, it means that for omega, which is angular velocity, the the model is okay. Yeah, the angular velocity controls the change in orientation, and the linear velocity controls the change in position. And so our next demo is basically trying to show why just relying on odometry is not a good idea. Again, we go to the demos page, and this time we run demo number 3. I hope at this point many people have their problem solved. So I just simply run the demo. Okay. So here the red agent is the real robot position, and blue is the robot position just based on odometry. Basically, we read some motion sensors, data from motion sensors, and try to locate the robot using the differential drive model that I provided in the slides. So as we see, the blue agent try has a pretty large error, like growing with time with respect to the with respect to the red robot, and the error goes larger and larger. As we see, it just hits the obstacles, go to the gray area. So the error is basically the robot position is becoming less and less accurate as we go forward. Uh, when I for the, I mean, this when you said for Kunal, when you said it worked, sometimes it works. Basically, it's a matter of what kind of sensors do you use. If your IMU or encoder is pretty accurate, it usually gives you good odometry output. And what is odometry? So odometry, as we discussed here, is using the motion sensors for estimating change of robot pose. Yeah, drift is always the problem. Yes, drift is basically accumulation of error during long time horizons. For mapping and localization classes, we can talk about it maybe after the slides. Why does the error increase with time? You can think of it as some kind of a small error which accumulates every time that you run the motors. Basically, as you could see in the demo, uh, every time there is a small deviation from the true pose, and this error, a small error, accumulates over time. So uh, the accumulation makes the error increase. there a way to reset the location? There is no way to resetting a location because we don't know the exact robot location. Otherwise, we could do that. That's the problem, basically. The robot location is unknown. The best thing you have access to is the initial robot location. As you see, the blue and red dots started at the same place. That tells that they start from the same location. Okay. So let's continue and try to talk about localization more. So localization is a method which takes control inputs like angular or linear velocities, the map, and robot observations, and tries to find the robot trajectory, the correct robot trajectory. In our case, we deal with angular and linear velocity occupancy grid, just like demo number 2, and LiDAR scans as we saw in demo number 1. And we try to generate correct robot trajectory like X, Y, and theta. Um, so for the sake of time, we don't have time to go deep to the math part of it. We use a method called particle filtering, which basically tries to maintain several hypotheses over robot position. We call each hypothesis a particle where there is a pose for each particle and also a respective weight, which basically the weights are basically the probability of each hypothesis, and they should sum to 1. So for example, in this picture, there is a robot, and the robot's position has some kind of probability distribution. The point is the probability distribution is bunch of points. Each bar, the short ones and the tall ones, all of them are just a hypothesis of a robot position, and the height of each bar tells about alpha, the weight or the probability of that hypothesis. So in this case, the robot kind of knows well where it is because there is a high probability near the true robot position. The particle filtering is has 2 steps: prediction step and update step. Where in prediction step, we basically try to predict the position of the particles, and in the update step, we try to incorporate observations like LiDAR observation in our case to correct the position of the particles. So in this case, let's say I have a prior probability for the particles, which is like this, kind of like a uniform over the space, and updates basically incorporates the observations. Let's say I have a sensor which tells me if I'm close to a door or not. So after the updates, I will have higher probabilities near doors because my sensor tells me that the robot is close to a door. So in the robot positions close to a door, the probability goes up. But if you think about it, still we cannot distinguish between doors. Still, we cannot say which door the robot is close to. And so these are the math parts. In our example, the way that we, sorry. Okay.
Sorry, can I interrupt for a second?
Yeah, sure.
Since we only have like 3-4 minutes, I just want to say a few words before we stop. You can still finish the slides later, but first I want to say thank you everyone for attending. This was our first time trying something like this, so please excuse that it wasn't super smooth for everyone. We are going to learn from today's exercise and try to make things smoother for next time in the future. So if you liked the idea, we're gonna have another event like this next Wednesday on April 7th at the same time, and we're gonna focus on a different part of robotics, and that's motion planning. And then we'll have one more the week after, again on Wednesday at 4 to 5:30, and that will focus on optimization. So again, we'll set up a GitHub repository, same way. So if you're excited about attending the other events, in the meantime, you can practice a bit more if you didn't manage to get the demos to run today. try to go through the instructions again more carefully, because I know a lot of the people who did not get things to work actually had not prepared. They started installing things right now. So doing it on the spot sometimes doesn't work. So start over fresh and try it, and do send us questions. And on the GitHub page itself, there is a place to ask questions or raise issues. That would probably be the best, so we can look at and remember it. So instead of kind of sending emails, it might be best if you post your question or issue directly on the GitHub page, because it will give us a track record of what we should try to fix. Yeah, and if you liked, so we're gonna follow up with the slides and the recording. We'll find a good way to share it with everyone. And yeah, so for next week, we'll prepare a bit more in terms of expecting errors for everyone on our side as well. And I hope that you get to learn a bit, and we'll be happy to share some classes next time also that you can take in UCSD to learn more about this topic. And maybe Arash, in the last minute, maybe you can just run the last demo on your end and explain what's going on in the demo instead of showing slides.
Sure. So for the last
Arash, you've muted yourself.
Thank you for telling me. Yeah, we try to run demo number 4, which is basically particle localization using particle filtering. So I will try to explain what's going on during the demo. Let's wait until the demo starts. Okay. So basically, as I mentioned, we try to model the robot position as a bunch of particles, and each particle score, I mean, that was the part I was going to say, each particle is scored based on its correlation with the map at its own position. So as we see, the robot sometimes gets lost because it just cannot find the best point, the point with the best correlation with the real robot position. But since it searches around the current position, sometimes if the search is wide enough, it can capture the current robot position again, as we saw there. And if you run like this demo with the previous demo, like together, you will see that basically doing particle filtering localization helps a lot to find the position of the robot, even if we have noise in our motion sensor measurements. So that's about it for particle filter localization. For the meetings, I think all of them are going to be recorded. Okay.
Yes. Hi. I'm Ashwin. I don't know if I introduced myself earlier. I'm one of the HKN officers. Huge thanks to Prof. Atanasov and Arash for today's presentation. It's really cool. In response to Unduap's question, all of these workshops, we are planning to record them and make them available to anyone. And so we will likely post that information on the Facebook event as well. So, you know, we will make sure that you get that information. But yeah, thank you guys all for coming today. We look forward to next Wednesday's workshop as well. And we hope to see you all there. HKN inductees, remember to hop in our Discord and ask for your checkoffs. I will handle that for you. Otherwise, have a great evening. And thanks again for coming.
Yeah, I can, sorry, last minute, I can show a quick preview of what we'll talk about next time for those of you who can stick around for one more minute, if that's okay. I can give you a very quick sneak peek into, so today we discussed how to do mapping. Next time we're gonna look at the planning algorithm. So this is the question of if you're in a given position and you want to go to a goal position, and now we've built our map of the environment. So blue here is the obstacles and black is the free space. We're going to look into these algorithms, which kind of figure out what is a safe way to go from the start to the goal location without crashing into obstacles. Yeah, so if this sounds interesting to you, we'll discuss this more next Wednesday. And I think that's all we've got. Ashwin, any final words?
Yeah, that's all. Again, I'm gonna hang around because you know, I'm gonna hang around for the HCAN people. If you need any help, message me here on the Discord. Otherwise, yeah, Professor and Arash, thank you again so much. I'll see you in class tomorrow, Professor. And yeah, that's all we have for today.